Equilibrium and thermodynamics. Equilibrium and thermodynamics are related to each other, and I have written an equation that relates the reaction quotient Q to delta G. And remember that delta G is Gibbs free energy. And so we have delta G equals the standard delta G, which we can get from calculating using the standard enthalpy and entropy values. Remember, delta G equals delta H minus T delta S. That's where this comes from, or you may actually look these values up in a table. They may exist for the reaction that we want. Plus the gas constant times temperature in Kelvin times the natural log of the reaction quotient. And so you can see you could use this reaction to determine what would happen at different temperatures to a particular reaction. But let's focus on and remember what delta G means when it's less than 0 or greater than 0 or negative and positive. Remember that when delta G is negative, that means that the reaction is spontaneous, and therefore it will go towards the products. It's product favored. Conversely, when delta G is positive, it's considered not spontaneous, and this reaction is reactant favored, as in it will either stay reactants, or if we had products, the reaction would go backwards. Now, there's an interesting number in between these two, right? So we have negative numbers over here, we have positive numbers over there, and there is a number that exists in between negative numbers and positive numbers, and that's 0. What happens when delta G is 0? Well, in that case, neither the forward reaction or the backward reaction is favored. Now, what's the definition of being at equilibrium? Well, that means that the forward reactions and the backward reactions are equal and opposite to each other. Therefore, when we have that, no net reaction is happening, and delta G will be 0. So, in that case, we could take the above reaction and write a new one and replace Q with K, our equilibrium constant. So if we have the delta G actually equaling 0, then we can write the reaction like this. And now, since we have delta G equal to 0, we know that Q is actually equal to K, so I've replaced that with K. And we could rearrange this particular equation to get perhaps a more useful expression. Let's move the RT over to the other side, and we'll have delta G over here still. And so if we move that over to the other side, we'll have a negative RT ln K. And that equals delta G under standard conditions. And then let's divide both sides by RT. Negative RT. And then let's see if we can simplify the ln of K just by raising it to the exponential, the natural exponential. And if we do that, we should get K equals E to the negative delta G standard condition divided by RT. This is a useful equation because now we can see that K is temperature dependent. If we change the temperature, we will change the value of K. And it really is only temperature dependent. That's the only thing that changes K. Now, delta G can sometimes change a little bit with temperature, but that won't be the major effect here. And still, we're changing the temperature, so then K would change. So what else can we learn from this particular expression? Well, if we were to graph what the value of K is versus the value of delta G at some temperature, then we would get a graph that would look something like this. So we'll have delta G and we'll have 0 right here. Now, K is on our y-axis and delta G is on our x-axis. And if we do that, over here is negative delta G values and over here is positive delta G values. Now, if we have a negative delta G, that means that the reaction is product favored. And if the reaction's product favored, that means that K is large. Remember, it's products over reactants. And so to get a larger value, we would want more products. That means product favored. And indeed, this reaction does support, or this equation does support that. If we have a negative number inside of delta G, that makes this exponential positive, and a positive exponential will be a larger number. So we'll start off over here at kind of a higher thing, and if I can draw an exponential curve here, something like this. Now, when it crosses through 0, this value for K is 1. And at that point, there's no real difference between being product favored or reactant favored. They're both about equally favored, and so that's why K is 1. Now, when delta G is less than 0, we see that K is greater than 1. And when delta G is bigger than 0, or not spontaneous reactions, we'll notice that K is less than 1. Now, again, K is never negative. This stays above 0 right here. It can get very close to 0. Some K's, some reactions are not very product favored. Some of them have K's that are 10 to the minus 30. That is a very small number, but it is still positive. And then, of course, you have reactions that have K's in the hundreds or thousands or millions. And those are very product favored, and they have a negative delta G to go along with it. So this is the relationship between equilibrium and thermodynamics. And we can explore some more of this when we look at what happens with changing temperature and how we can use that to our advantage to determine other thermodynamic properties.